Hello learners, in today's class we'll discuss the different type of cost function and we'll discuss different type of regularization technique and R square and adjusted R square. Okay, so let's start class. Okay. So in today's agenda, so we first discussed R square, then we discuss adjusted R square, then mean square error, then mean absolute error, okay, then binary cross interpolus that is log-loss, categorical cross interpolus, then ridge regression, then lasso regression, then elastic net regression. Okay, it is the agenda of today's class. Okay, so we'll see what is R square. R square is a statistical measure that depends the proportion of variance in the dependent variable. Dependent variable is the target variable. Okay, that is explained by the independent variable. Independent variable matlab number of features. Okay, so R square is a statistical measure. So it measures the variance between dependent variable and independent variable. Okay, and it ranges for 0 to 1. Okay, R square ranges from 0 to 1. Okay, and where 0 indicate that model does not explain any of the variability, okay, of the response data around its mean, and 1 indicate that the model explain all the variability of the response data around its mean. So we see the formula of R square, that is, so R square equal to 1 minus SSRES whole divided by SS total. Okay, so formula of R square. So here SSRES is SSRES equal to, so sum of square residual. Sum of square residual. Okay. So SSR is equal to summation of I equal to 1 to n and actual minus predicate whole square. Okay. And SS total. We'll see what is SSRES and what is SL total. SS total means sum of square total. Sum of, okay, square total. Okay. So here summation I equal to 1 to n, formula is same. Okay. Yi minus yi actual minus predicate whole square. Okay. So here you notice what is SSRES and what is SS. Okay. Suppose you notice the line of linear regression, that is a line is this. Okay. Okay. It is your SSRES. Okay. So it is SSRES. And one line is this, that is like this, and it is your SS total. SS total. If you calculate the actual minus predicate, okay, for this line, so it is SSRES. Okay. If you calculate for this line, that is SS total. So here you notice in adjusted R, sorry, in R square, so we calculate this by this formula, that is R square equal to 1 minus SSRES whole divided by SS total. So SSRES is sum of square residual, that is the formula of SSRES, and that is the formula of SS total. So here you notice The value range is between 0 to 1. Okay, the value range is 0 to 1. If it is best fit line, if it is best fit line, okay, if it is best fit line, then SS total greater than, much greater than SS RS. Okay, so R square value is very small, that is 1. Okay, so if you conclude that if SSRES, okay, greater than equal to SS total, this implies R square is negative value. Okay, here notice if SSRS is greater than SS total, then R square is a negative value. Okay, so okay, then for some demerit, we will notice adjusted R square. What is the demerit in R square? If you notice, I will give you a practical example. Suppose you want to predict the house price prediction. House price predict. Okay, using linear regression. Okay, if you notice, okay, suppose the features are the number of bedroom, okay, number of room, okay. Then second feature is location, okay. Then third feature is room size, okay. If you calculate for these features, the linear regression line, if you notice, number of room does not depend much, okay. Room size given, so number of room does not depend. Okay, it is a independent variable for predict the house price. Okay, so for reducing the number of room features, we will use adjusted R square. We will use adjusted R square. So you notice what is adjusted R square. So here you notice adjusted R square is a modification of R square that takes into account the number of independent variable in the model. It penalizes the addition of unnecessary variable that don't significantly contribute to explaining the variance in the dependent variable. So you directly notice adjusted R square formula, that is adjusted R square equal to 1 minus R square, okay, into n minus 1 whole divided by n minus p minus 1. Here n is your number of data point. Okay, how many data is present in the data set. Okay, and R square, you know what is R square. Okay, so R square formula. Okay, and here one variable is present, that is p. So p equal to number of independent features. Okay. So it is the formula of adjusted R square. For disadvantage of R square, we will use adjusted R square. Adjusted R square is used for to reduce the independent features. Okay. So the adjusted R square value will always be less than or equal to R square. Okay. R adjusted R square value, okay, is always less than or equal to R square. Okay, and it increases only the new variable improve the model more than would be expected chance. Okay, while R2 measures the goodness of fit, R square is measured the goodness of fit. Okay, of the model. Adjusted R square adjust for number of predictor in the model. Okay, so providing a more accurate assessment of the model's explanatory power. Okay, adjusted R square is often preferred when comparing model with different number of predictor to avoid overfitting or including irrelevant variable. Okay, so what is overfitting? We'll discuss later. Okay, so we'll notice next topic, that is types of cost function. Okay, so here types of cost function. So we'll discuss cost function, also known as a loss function. Okay, or objective function. Okay, cost function and loss function and objective function all are same. Is a recur component used to quantify the difference between predicate value and actual value. Here we will discuss some of the cost function or loss function or objective function, that is mean square error, second is mean absolute error, third one is binary cross entropy loss, that is log loss, and last one is categorical cross entropy loss. So directly we'll discuss mean square error. Okay. So here mean square error is calculate the average of the square difference between predicted value and actual value. So here you notice mean square error we'll discuss also in regression, linear regression, that is 1 by n summation I equal to 1 to n actual minus predicted, okay, whole square. Okay, that is it is a quadratic function and convex function. So advantage of mean square error general use. Okay, advantage is first one is mm, okay. So first one is equation is differentiable. Equation is differentiable. Okay. And second advantage is it has only one local and global minima. It has only one local and global minima. Okay, so how? So if you draw the linear regression, okay, 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 so the curve will be like this. Okay, so it has one local minima and maxima. It is a local minima. Okay, so two advantages. First one is equation is differentiable. Second one is it has only one local and global minima. For some disadvantage is there, so that is disadvantage is okay. So disadvantage is not robust to outlier, not robust to outlier. Okay, suppose you draw the line, okay, like this for some data point, that is for some data point like this, okay, okay. If some outlier is present, suppose one of the outlier present, some outlier here. Okay, so it is the disadvantage of mean square error. If you use the mean square error, then it is not robust to outlier. Okay, so for this advantage, we will go second method, that is mean absolute error. Okay, so similar to mean square error, it is more similar to mean square, but calculate the average of absolute difference between predicted value and actual value. Okay, so the formula of mean absolute error is so 1 by n summation I equal to 1 to n, Y, that is actual minus predicted absolute value. Okay, it is the formula of mean absolute error. So what is the advantage of in mean absolute error? Okay, we'll discuss. First one is it is robust to outlier. Okay, and second advantage is units are same. Okay, units are same. And disadvantage of mean absolute error is okay. So it is convergence. It will take time. For convergence, it will take time. It will take time. Okay. So if you notice, okay, suppose the if you draw for mean absolute error, you will notice some outlier in mean square error. The line is like this. Okay, the line is like this. Okay, for some point like this. Okay, so if some outlier is present here, okay, it is not possible in mean square error. But in mean absolute error, the line is like this. Okay, and it is robust to outlier. So it is the main advantage of mean absolute error. And it is not convergence, it will take time. So mean absolute error of disadvantage is convergence, it will take time. If you see, okay, the point like this, okay, so for convergence, it will take time. Okay, then we will see binary cross entropy loss. Okay, so it is also called log loss function. Okay, so in this cost function used in binary classification problem, that is some yes no problem, or some example that is spam or not spam used in mail. Okay, for measure the difference between predicted probabilities and actual binary level. So binary cross entropy formula is okay, binary cross entropy equal to minus 1 by n summation I to 1 to n yi log up yi plus 1 minus yi into log of 1 minus y. Okay, it is the formula of binary cross entropy loss. And it is used for only binary classification problem. Okay, for multi-class classification problem, we will discuss categorical cross entropy loss. Okay, you do in multi-class classification problem and similar to binary cross entropy, but extended to multiple class, that is more than two. So here we discuss categorical cross entropy loss. So categorical cross entropy equal to minus summation I equal to 1 to n yi log of yi. Okay, it is the formula of categorical cross entropy loss. Okay, so these are the sum of the commonly used cost function in machine learning. Okay, it's important to choose the appropriate cost function based on the specific text and the nature of the data. Additionally, regularization technique is the most important part of machine learning. Example L1 regulation and L2 regulation can be applied to cost function to prevent overfitting and improve generalization. So now we will discuss the regularization technique. That is first one is ridge regression. Okay, that is also called L1 sorry L2 regularization. Okay. Okay, so ridge regression is a linear regression technique that asks a regularization term that is L2 penalty to the linear regression cost function. Okay, ridge regression helps to shrink the coefficient towards zero. Okay, coefficient towards zero. Okay, but does not set them exactly to zero. It will never equal to zero. Okay, never equal to 0. It is useful for reducing the impact of multi-collinearity in the dataset. Okay, so we discuss ridge regression. So it is the use for generally reduce overfitting. Okay, reduce overfitting. Suppose it is your dataset. Dataset. You divide the dataset as training and testing. Training and testing. Okay. Always remember for dividing the dataset, training and testing ratio is 7 into 3 or 8 into 2. That is training for 70% and testing for 30% or 80% or 20%. Like this. So when you divide the dataset in training and testing, if you notice that training accuracy, training accuracy, okay, is 93%. Suppose and testing accuracy is 50%, very less. Okay, so it is the overfitting. If you notice, testing accuracy is maximum, sorry, training accuracy is maximum and testing accuracy is minimum, then it is overfitting. Okay, so here the cost function is for reduce overfitting, that is 1 by n summation I equal to 1 to n, that is actual minus predicate square plus it is the formula of mean square error. Okay, plus lambda into summation I equal to 1 to n slope square. Okay, lambda summation I equal to 1 to n slope square. Here lambda equal to hyperparameter. Okay, and you notice lambda equal to 1, 2, 3, dot, dot. Okay, so if you notice the mm, okay, so okay, okay. So if you draw this line like this, okay, it is for lambda equal to 0. And if lambda increases, then it is for lambda equal to 10. And it is for lambda equal to 20. Okay, when lambda increases, okay, then theta decreases. Theta means that is the slope. Okay, and it will not become zero. Okay, so it is the regression. So now we will discuss lasso regression. That is L1 regularization. That is L1 regularization. Okay. What is the full form of lasso? That is least absolute shrinking and selection operator. So lasso regression is another linear regression technique that adds a regularization term, that is L1 penalty, to the linear regression cost function. Okay, the regularization term penalty large coefficient by adding the absolute sum of the coefficient multiple by regularization parameter, that is alpha, to the cost function. So here you notice, and generally it is used for feature selection. Okay, L1 regularization is used for reduce, L2 regularization used for reduce overfitting, and L1 regularization used for feature selection. And the cost function is mm, 1 by n summation I equal to 1 to n, that is formula for mean square error, okay, plus lambda into summation I equal to 1 to n, that is slope. Okay, so here you notice, like, we'll draw the diagram shows like this. Okay, it is for lambda equal to 0, same diagram like this, little bit difference, that is lambda equal to 10, lambda equal to 30. Okay, here you notice that is h theta of x, okay, equal to theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3. So the value of theta 0 is 0.52 plus 0.65 x1, okay, plus theta 2 is 1.5 x2 plus 0.2x. That is the important of features. Here x1 is one feature and x2 is another feature and x3 is one feature. So the participate of x1 feature is 0.65, second one is 1.5 and third feature is 0.2. So the least important feature is x3. So here the least important feature is x3, that is 0.2 x3. Okay, so for this, here you notice a theta of x equal to 0.52 plus 0.50x. The value is slightly decreasing. Okay, then 1.3x2, then 0.1x3. After some time, it will be 0.52 plus 0.40x1 plus 1.1x2 plus 0 into x3. And the third feature is reduce from the cost function. Okay, so the accuracy will increase it. So for feature selection, we'll use for lasso regression. Okay, so here we study two type of regression technique. First one is ridge regression, second one is lasso regression. Ridge regression generally used for the reduce overfitting, and lasso regression generally used for the feature selection. Okay, and lasso regression not only helps in the feature selection by setting some coefficient to exactly 0, but also perform variable selection by choosing only the most important feature. Okay, so for next, we'll discuss elastic net regression. It is generally combination of R1 regression plus, sorry, L1 regression. It is the combination of L1 regression plus L2 regularization. Okay, elastic net regression is a combination of reach and lasso regression technique. It adds both L1 and L2 penalty to the linear regression cost function. Okay, so here you notice elastic net regression is generally it is the combination of L1 and L2. Okay, so here L1 is used for that is reduce overfitting, overfitting. Okay, that is reach regression, and for feature selection, we will use lasso regression. Okay, so here the cost function is combination of reach and lasso. So the cost function is that is mean square error, that is 1 by n summation I equal to 1 to n actual minus predicted whole square plus lambda 1. Okay, for reduce overfitting, that is reach summation I equal to 1 to n. Okay, slope square plus lambda 2 summation I equal to 1 to n, that is slope. So it is your mean square error, and second one is for reach regression for overfitting, reduce overfitting, and third term is for feature selection. Okay. So elastic net regression combine the benefit of reach regression, that is for reduce overfitting or handle multi-collinearity also, and lasso regression perform good feature selection. Okay, making it a more flexible and robust, especially when dealing with data set with the high dimensional feature and multi-collinearity. Will use elastic net regression. If we use for reduce overfitting, that is ridge regression. For feature selection, we will use for lasso. For two, that is for reduce overfitting and feature selection, we will use elastic net regression. Okay. So, okay. So in next class, we will cover your that is some polynomial regression, that is logistic regression, polynomial regression, and logistic regression, and some performance metrics. Okay, performance metrics. After that, we'll direct go to decision tree, that is supervised learning. So thank you.